Welcome back. At long last, today we'll begin studying bivariate or two-variable statistical tests. We'll start with the case of two categorical variables. Specifically, we'll be focusing on the chi-square statistic, the capital Greek chi, which looks like a curly X. And the chi-square statistic is used to answer the question, is there a relationship between two variables in a contingency table or crosstab? That is there a relationship between two nominal or categorical variables? The trick is, as is often the case, figuring out what we compare our results to. So let's look at a 2x2 table from the 2012 GSS to examine whether support for legalized marijuana varied by sex. The question was asked as a simple yes-no, so the size of the table will be two sexes by two responses, for a total of 4 cells. Here's the table at the top, where it says observed frequencies. You can see that 735 males said yes, marijuana should be made legal, while 753 females said yes, 616 males said no, 917 females said no. Now, there are a number of ways you might try and figure out if there's anything to see here. Descriptively, there are at least 3 ways to take stock of it without moving as far as statistics. The first is simply by comparing the proportion of people in each cell. This is referred to as the total percent. And while it makes intuitive sense, it suffers from a major problem. The total percent does nothing to account for the size of each group. So in our table, for example, the total percent in male yes and female yes is nearly identical. But there are over 300 more women than men in the sample, meaning that those proportions have very different meanings. Total percentages are useful when you want to understand the overall makeup of a sample or a population, more than to look at the relationship between variables. So one solution to the problem above might be to compare the proportion of each group, each column, in each row. These are called column percentages. So in our table, the column percent for male yes would be 735 out of 1351. These are totals on the edges here, or 55%. That is, 55% of the men in our observed sample of GSS 2012 supported legalized marijuana. By contrast, the higher number, 753 in the female column, only makes up 45% of the women in the sample because of the larger number of women in the sample. Now, in deciding, the same thing can be done with row percentages, right? You could do 735 out of 1488, and so on. That answers the question, what portion of the row are in a given column? So in our sample, we see that yes is fairly evenly split between men and women, but no is around 60% women, 40% men. In deciding what type of percentage to look at, you need to consider what your underlying question is. If you're asking, are men or women more likely to support legalization in general, that would be a column percent. We want to see the percentage of men versus the percentage of women who say yes and who say no. If you want to know, is legalization gaining more support from a specific sex, that's a row percent. We could see that actually, if this was balanced in the population, say for example, if we were looking at religious groups and we saw Christians had more or less support, then that might tell us that in the whole population, those people are making up a large part of the people who are making the case for legalized marijuana. And if your question is what proportion of the population has a specific combination, for example, if rows were gender and columns were sex, and we wanted to know how sex and gender combined in the population, then you're looking for total percents. Now, having considered how best to describe our data, the next question a good statistician asks is, how can I find out if these differences are likely to be due to chance? We could simply compare each cell to the average count, that is the total over the cells, so 3021 over 4 would be 755 in our table. But this has the same problem as total percents. It doesn't tell us about the relationship, because it doesn't account for sample size unless you have a balanced experiment with the same number of cases in each group. Instead, we need to find out what the cell counts would be if each row were distributed randomly across the columns and each column distributed randomly across the rows. Now, you may not understand how to do that simultaneously in an intuitive sense, but what we do is we multiply the total number in each row by the total number in that column. So for the men, yes, we would multiply 1488 times 1351 and then we divide it by 3021. And you see down here, in the expected frequencies, the expected frequency there is 665.4. And we do that for all of them, and what do you notice? You notice that the row sums and the column sums stay the same, as does the total sum, which is what we want to see. So this matrix on the bottom comprises what we actually call our model. It's a random assortment model that the only assumption is that the proportions in the population of each individual variable match the proportions in the sample. Now we're most of the way to our chi-square statistic. To get the chi-square statistic, take the cell squared deviation, that is the observed minus the expected, and divide that by the expected value. So we would take 735 minus 665.4 for the numerator. We'd divide, and then square it. We would divide by 665.4. And we would do that for all the cells together and add it up. That's the sum from I to n, right? We know, yeah, equals 1 to n. We recognize that. Remember, the chi-square is an omnibus statistic. That means it's one number that summarizes an entire equation or an entire sample or an entire table. Now, we can compare the chi-square statistics to a critical value in a chi-square table. Degrees of freedom is rows minus 1 times columns minus 1. To see why this is, think back to the expected values here. For a 2x2 table, once we have a value in a row, if we know the total, then we also know the value in the other cell in the row, and the value in the other cell in the column. And once we know those, we'll know what's left for this one. If you had a 3x2 table, you would need 1, 2, 3 minimum. That is 3 times 2, which is 6, minus, or I'm sorry, 3 minus 1 times 2 minus 1, or 3. Now, something else may seem odd. If you look at the chi-square table, which you'll need to get familiar with, although usually you'll be doing it on a computer, you'll discover that the more degrees of freedom you have, the higher the critical values necessary for significance, which is the opposite of what we've seen before. This happens because we're asking the question the opposite way of what we usually do. We're not constructing a model to try and improve fit. We're using a baseline model and comparing the empirical data to it to see, is it different? There are ways you can standardize very similarly to a normal z-score, produce z-scores for a cell. There are other ways to adjust the chi-square test when its assumptions, that is, its independent errors and the normal the two assumptions of the chi-square test, which are independent errors, that is, the count in one cell doesn't overlap with the count in the other. You can't be in two cells, otherwise you can't do a chi-square. And a normal sampling distribution, that is, you can use the central limit theorem, are unmet. But for the most part, chi-square statistics are used as a kind of baseline, first pass, at determining whether two or more variables are related. Luckily for us, they're quick and easy with the computer. It's a great way to start before you go all the way down the road of regression and things. So that's all for now. Remember, chi-square uses observed and expected. It's an omnibus test of the whole table, and it tests whether the cell counts are different than what we would expect randomly. I'll talk more next time about other approaches to studying two-variable relationships, bivariate relationships, particularly Pearson's correlation coefficient, R, which we've already encountered. Until then, thanks for watching, and see you soon.